So next we're going to find the first moment of area, and we know the terminus. This is the terminal, okay? So terminal 1, terminal 2, terminal 3, terminal 4, and you will have also terminal 5, okay? So terminal 3 is not linked to terminal 1, terminal 2 is not linked to terminal 4. So the first moment of area that we're going to take is this area over here. And we are going to take Qy, which correspond to the width, depth, x bar. Okay. So the first, so if the force, so you ask Eugene, which is the width, which is, so you will know that we are looking at I, y, right? Right. So y, this is the axis, so this will be our width, and this distance over here will be our what? Depth. Okay. So the width, which we already find out, is 11.8 times 10 to the power minus 3, right? Now the depth, we know the distance from here to here is 75 millimeters. It's given in the question. So if you look at the question, that is where I get the 75 millimeters. Okay. So the depth now is 0.075, right? And then the y bar is equal to BF over 2, right? So this distance is, I think our BF, if I'm not wrong, is 0.205. Let me check. BF, I don't want to get it wrong. BF, oh, lucky I checked, 0.166. Okay, so we know that this is 0.166, right? The entire length. So the y bar is equal to 0.166 divided by 2 minus by 0.075 divided by 2. Okay. So this will be equal. I'm not saying the first moment of area is difficult, but you have to be careful. Okay. So it's equal to 40. We get 40.267. Let me the width, the depth. Yep. So I get the width, the depth. Yep. So 40. Let me press my calculator again. Yep. 40.268 times 10 to the power minus 6. Right. And from here, once we got that, it's also straightforward. So shear Zx is equal to Vy, which is 16 times 10 to the power 3, multiplied by Qy. This is in meters cubed, by the way. So 40.268 times 10 to the power minus 6. And then we divide by Iyy, 9.03. 9.03 times 10 to the power minus 6. And then the thickness is 11.8 times 10 to the power minus 3. Okay. So 16 power 3 times 40.268 power minus 6 divided by 9.03 power minus 6 divided by 11.8 power minus 3. So I get 6 point, wait, did I get my, this is for Vx. 40 point, yeah, 6.04. I'll do it again. Yep, 6 point 0.047 times 10 to the power 6 Pascal. Okay, and I want you to take note of the direction of the shear now. Because it's going from right to left, you have to put in the direction. Okay, now I'm going to do exactly at the side. Okay, and at the side, now we are going to do Vy. Okay, so Vy. And we know that Vy, we did find out what the value was. Let me, it's 25 times 10 to the power 3. So this is our element A. And then we design the shear flow. Right, the shear flow goes like this. And then, so the area of interest is up to here, right? White flange analysis. So we know that again, this is shear, Z plane, X direction is equal to Vy over Ixx Qx divided by T. Okay. So we know that Vy is 25. We can determine our Ixx from the table is 40.8. And then we know the thickness, right? We know that this is going to be thickness. So it's also 11.8. Okay, the thickness is 11.8. Times 10 to the power minus 3 meters. So the next thing is how to determine the Ixx. No, sorry, Qx. So now we know, because we are looking at Ixx, right? Xx is the axis of interest. So this is the width. And over here, this is the what? Depth. Okay. So the width we know is 0.075. The depth we know is 11.8 times 10 to the power minus 3. Now the y bar is d. Okay, so d is what? 0.205 divided by 2. Okay, so this is 0.205. Right, so 0.205 divided by 2 minus 11.8 times 10 to the power minus 3 divided by 2. Okay. Why? Because the distance from here to here, this is equal to 11.8 times 10 to the power minus 3 divided by 2. And then the distance from here to here, this is 0.205 divided by 2. So in fact, this distance that I'm drawing now, this is your y bar. Okay. So from here, this will be equal to 0.205 divided by 0.205 divided by 2 minus 11.8 power minus 3 divided by 2. Wait, 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.83 times by 0.075 is equal to, I get 85.491 times 10 to the power minus 6 meter cube. Okay. So now we can find out what is our shear ZX. So this will be equal to our Vy, 25 times 10 to the power 3, 85.491 times 10 to the power minus 6, divide by Ixx, 40.8 times 10 to the power minus 6, and then the thickness is 11.8 times 10 to the power minus 3. So you don't need to divide by 2 because it's a white flange. It's not a box beam. Okay, so 25 power 3 times by 85.491 power minus 6 divided by 40.8 power minus 6 divided by 11.8 power minus 3 is 4.439. Okay, 4.439 times 10 to the power 6 Pascal. And then if you look at the shear, right, the direction is going towards the right. Okay. So now we have a shear, both shear ZX 6.047 going towards the left. And then the other one is 4.439 times 10 to the power 6 going towards the right. Okay. So now coming back to this figure down here, let me copy this figure. And this is where this is getting important. Okay. So we know the 6.047, right, is going in that direction. So the 6.047. So the 6.047 is due to our Vx. Okay, so when Vx is equal to 16 times 10 to the power 3 Newton, we know that shear Zx due to Vx is equal to 6.047 times 10 to the power 6 Pascal. And the direction is going this side. Okay. However, when we have Vy is equal to 25 times 10, 25 times 10 to the power 3 Newton, right? Our shear Zx due to Vy is equal to 4.439 times 10 to the power 6 Pascal. But the direction is opposite. Okay. So the true direction, so if you were to, because one is going up, the one is going down, right? So the right value for shear xy, okay, this is the wrong direction. Okay, the right direction is going up this way, right? And why the right direction is going up that way? Because this shear, the shear xz or zx, sorry, with shear intersecting, yep, zx is equal to 6.047 minus by 4.439. So the magnitude value, right, is equal to 6.047 minus 4.439 is equal to 1.608 times 10 to the power 6 Pascal. So that is the direction of the shear stress. Okay, and this one, this direction is not here. Now this is the direction of the shear. Okay, so this is how your element will look like now. Okay, so this is our element A. Okay, so that's your element A. So if you look at homework number 8, okay, I want you to draw the element, the stress state of the element, and this is the way you do it. Okay, now anyone, any questions so far before I do element B? Anyone? The it's not difficult. The complexity is you have to remember your stress induced by bending moment and also stress induced by shears or by the shear force. Okay, and this one does not have torque. Later on, I'll do an example that has torque. Okay, so more stress component coming in. Okay, right. If no one have any question for now, let's look at element B. Okay, let's look at element B. So element B is a different location, but the stresses are by no means sorry, element B is at a different location, but the loads are still the same, but the stresses will change because the position is not the same. So I'm going to copy this whole thing. And now we are going to look at stresses. Okay, stresses on element B. Okay. So we know that we are going to write stress Y, sorry, stress Z at element B is equal to minus PZ over A, because we know that the 100 kilonewton is going to induce a compression. So down here, we don't know yet, not to worry. So we have mx over Ixx multiplied by y plus or minus my over Iyy multiplied by x. Right. So the first term is pretty straightforward. Minus 100 times 10 to the power 3. And the area is 5320. So next we look at moment. So this is moment in our x, and moment in our x is equal to the stresses at point B is going to be equal to 0. Okay. Why is it equal to 0?